Hello, let me introduce myself. My name is Garrett Moss, and I'm going to tell a little bit about my story. I have like a little quote from John Lennon's song, "Life is what happens to you while you're busy making other plans." And also was the theme of the movie Mr. Holland's Opus. So I got my bachelor's degree in biology in the 1970s, and then around 1979, I got a dual master's in biomedical engineering at chemical engineering, but the major focus I had was on biomedical engineering. And so I'd applied to a company called Medtronic, very big in biomedical engineering. And I thought I might have a good chance there because, I did a pretty good master's thesis. My master's thesis was developing a glucose sensor. You see it on the right-hand side. This is kind of an image top view and a cross-sectional view of this image sensor. I used something called a Q matrix. Didn't do it quite right, but the professors didn't know. It actually worked as modeled. And that was a big success. And that was the very first time Arizona State University sold its intellectual property, a patent to industry, sold it to Boehringer Ingelheim. And that actually made the front page of the local newspaper, the Arizona Republic. There you see my two professors, Dr. Eric Gimbo and Dr. Stowe, looking at that glucose sensor that I helped develop and design, and it worked as modeled for a glucose sensor. So I applied to that job at Medtronic. And they looked over my resume and they said, "You have good grades, but no experience." And they turned me down, and I was rather disappointed. So instead, I got hired by Motorola. But I had a severe disadvantage relative to the engineers at Motorola. Pretty much most of the other engineers were electrical engineers, and here I was, a biomedical engineer in a sea of electrical engineers. And I was asking stupid questions like, what's a transistor? So mostly I was at a disadvantage, but I did have one advantage because most of the electrical engineers had no background in statistics, whereas me, with my bachelor's in biology and master's in biomedical engineering, I had to use statistics to draw conclusions from any of my lab work. So, that of the blind, one-eyed man escaped. I kind of became the king of statistics. That turned out to be very valuable because the timing. I joined Motorola in 1979, May 1979, but shortly before that, there was an officers' meeting. The vice presidents and president and CMO of Motorola had met together, and one of the vice presidents very boldly made a statement. During the 1979 annual Motorola officer meeting, this vice president, Art Sundry, said, "Motorola's quality stinks." And what it's referring to is Motorola had sold their Quasar brand of television sets to Matsushita a few years earlier. And Matsushita was able to improve their quality and reduce their defects, but they kept essentially the same manufacturing process, essentially the same operators. The only thing that really changed was the leadership. So that provided a startling, really eye-opening picture that the leadership directly influenced the quality of products. And so when Art Sundry made that statement, he was basically saying Motorola's quality stinks, and we, the officers of Motorola, we are responsible. So that stirred up a whole bunch of talk in Motorola around the time I joined. So I started bringing statistics, and we had some pretty nice successes in improving the quality and yield of our products. And so we had a kind of a network of engineers who were kind of combining probably statistics with engineering modeling. Tony Alvarez, Mike Clayton, myself, and a guy we hired from the CIA, Barrison Skip Weed. And we started having these successes, and we caught the attention of the headquarters of Motorola in Schaumburg, Illinois, near Chicago, Illinois, and they asked us to teach classes. So the four of us started flying up to Chicago teaching classes, along with a couple of outside consultants we brought in, Doreen Shingen and Dennis Sean. So we would fly from Phoenix, Arizona, show on this map, to Chicago, Illinois, O'Hare Airport, Schaumburg, flag of Motorola. Here's the Schaumburg flag where we were taught the classes. And one of the students in the class was a gentleman by the name of Bill Smith. He was a quality engineer. He basically is the man who coined the term Six Sigma, and I'll explain why on the next slide. Unfortunately, I'm going to have it from a friend of ours, close associate of him, John Forsberg, rather than Bill Smith, because unfortunately, shortly after all these events, Bill Smith unfortunately passed away. So John Forsberg recalling his work with Bill Smith. We were trying to improve the overall reliability of Motorola products, and many of the failures they had in the reliability evaluation lab matched the returns they were getting from the field from customers being returned. In both cases, most of these failures were early life failure due to latent defects, due to quality issues. He's referring to the bathtub curve. Here's a picture of the bathtub curve. It's called that because it looks like a cross-section of bathtub. It has three regions: early life failures, useful life, random chance failures, and wear out phase of reliability. And these failures were in the early life failure on the left-hand side of this graph due to quality issues. And when they analyzed these quality issues due to parts failing in the reliability lab and failing in the field, Bill was able to find that most of them were, as shown in this lower left kind of graph, distributions where they were really close to the spec limits. The spec limits are represented by the up and down kind of goalposts, the blue lines up and down. And so things outside the spec limit show up in red, and inside the spec limit show up in blue, and parts very, very close to spec limits. Those are the ones that were the early dot failures, either of the customers or in the reliability lab. So understanding this, Bill Smith proposed a solution. What if we were able to design our processes and our products so that our distribution does not get close to the spec limits, that our need is 6 standard deviations away from the lower spec limit, and similarly 6 standard deviations away from the upper spec limit. The Greek letter that we use for standard deviation is sigma. So 6 sigma away, the mean being 6 sigma away from the lower spec limit, LSL, 6 standard deviation, 6 sigma away from the upper spec limit, USL. And 6 Sigma iterated, so we called this 6 Sigma, which became a Motorola trademark. And he got rather excited about the potential for this. We had an open door policy at Motorola. Anybody could set up an appointment and meet with anybody else. He set up an appointment and met with the CEO of Motorola, Bob Galvin, and Bob Galvin got very excited about this. And a few years later, it became a program within Motorola. A few years later, Motorola won the Malcolm Baldrige Award for Quality. And in the excitement of doing that, Bob Galvin decided to share 6 Sigma with the world. And I have the first published article, the first published article on 6 Sigma. You see in the upper left, published in August 1987. That's actually the second publication. The first one was a little bit earlier in the editor's note you have in the lower part of this. It was called System Moments Method, also called Variance Transmission. Here I call it System Moments Method for Reducing Fabrication Variability by yours truly, Eric Seamonts at Motorola. In that article, we had some really good success stories that I was captured showing this method of combining probability statistics with engineering modeling. You see a picture of me back when I had more hair and had a mustache. So basically, what we were using, this was the very first design this was the beginning of what became design for 6 Sigma. The idea of melding or combining engineering modeling with probabilistic thinking. Another term for probabilistic thinking is stochastic modeling. So predictive engineering, stochastic engineering are kind of synonyms. The idea is you have expectations from your customers, from your stakeholders. You make them measurable, measure requirements. You flow them down to things that affect them, control factors, things you control, noise factors you think you don't completely control that affect these measurable requirements. You create an engineering model relating your measurable requirements as your outputs to your control and noise factors as inputs. That engineering model at that point is deterministic. The inputs determine your outputs. But we don't control everything. So if we bring in that variability represented by these little blue distributions, we can take this engineering model from being deterministic to being probabilistic or stochastic. And that is stochastic engineering, also called predictive engineering. And the ways to make that engineering model stochastic, probabilistic, Monte Carlo simulation, variance transmission, also called the system moments method, discrete event simulation, and Bayesian methods. So the first time we applied that was a team project on a family of integrated circuits called a FACT CMOS logic family. In the upper left, you see we were able to predict the yield as a function of manufacturing parameters, L effective, the distance from the source and drain of a transistor, the threshold voltage, the turn-on voltage for the transistor, and we were running around 57% yield right on this graph over here. And we will show that. Now we can do what ifs. What if we change the design of the output buffer to part of the circuit design? Wow, that would flatten out the area where the yield's greater than 90%, shown in green. Well, what if we change the process, like change the substrate open? That changed a different portion of this graph to be greater than 90%, shown in green. What if we did both, the output buffer design change and the change in process substrate jumping? Wow, you get an area where the yield was in the upper 90s, no matter what you did, robust against variation in manufacturing L effective and threshold voltage. And that's what we did. And the yield went from 56% to the upper 90s. And we did this for 57 other new products. All 57 of them were first pass successes and were introduced in record time, 28 weeks of Motorola record, led to hundreds of millions of dollars in sales, hundreds of millions of dollars of profits. And we presented this at an internal competition within Motorola. 6,000 teams competed, and out of those 6,000 teams, we won the gold medal in this Total Customer Satisfaction TCS competition. Later on at Motorola, a vice president, Bob Epson, decided to use this approach designed for 6 Sigma on all new products in Motorola Government and Public Safety Group, which is now Motorola Solutions. And this is his chart over here that you're showing up here. The number of post-launch issues to the left is before starting using DFSS on all the products. Bob Epson put a line in the sand, represented by the dashed line. Starting now, all new products will use design for 6 Sigma. You see a reduction, and here I kind of dramatize it. I analyze it using a statistical method of black spot, median of 7, down to a median of 2, 3.5-fold reduction in the number of post-wash issues. And that's statistically significant no matter how you looked at it. So around that time, Motorola started breaking into pieces, and I was in the corporate group, which no longer existed. So I wrote a book called Applying Design for Six Sigma to Software and Hardware Systems. And a few days after I got my copy, I interviewed at Motorola, pulled out the book when I was asked a question about any of this. I'll show you where it is in this book I just wrote, and I got hired at Medtronic. I told them I applied for a job there 30 years earlier. They said I had good grades but no experience. Now, 30 years later, I have 30 years of experience. And so I worked there for about 12 years, and then I eventually retired from Medtronic. But in that time, we applied predictive engineering, stochastic engineering to a whole bunch of new products in Medtronic cardiac rhythm, heart failure, CRHF group. And we were able to drop development time of new products by about a year for both iterative programs and totally new platform programs, dropped it about a year. Similarly, in Medtronic restorative therapy group that works on systems that work on neurological issues and issues in the spine, we're able to improve our quality, reduce our number of field corrective actions, kind of improve that quality by about 70%. They use predictive engineering for our project managers, and they got to 92% of the projects being on time and on budget. And similarly, we were able to reduce development time by about a year. So basically, that's kind of the story of using predictive engineering. That's also called stochastic engineering. It's a part of Design for Six Sigma. First at Motorola, then at Medtronic, and then a couple years ago, I retired from Medtronic. It was kind of time, but I'm not the kind of person to retire gracefully and just watch TV and golf or whatever else. So I've been teaching classes and coaching people at all sorts of companies about stochastic engineering. And that's what we're trying to learn about now. And then I wrote a book around the time I retired called Flawless Launches, Profitable Products. So I hope you find this background interesting, but a whole bunch of success stories we'll be sharing with you in the course of this program. Good luck and have a wonderful day.